Every star, every galaxy, every atom in the universe shares a common origin. It all began 13.8 billion years ago with the Big Bang. But how do we know this? What evidence do we have of the universe's fiery birth? The answer lies in the cosmic microwave background radiation, or CMB, a faint glow of light that is both ancient and profound. It's the closest thing we have to a time machine, taking us back to the infancy of the cosmos. Hi, and welcome to Stellar Studies, your window to the universe. Let's explore the universe's first light, the cosmic microwave background radiation. Chapter 1. The Universe as a Plasma. Why Light Couldn't Travel. The Big Bang wasn't an explosion in space. It was an expansion of space. In its first fractions of a second, the universe was an unimaginably hot and dense singularity, filled with a soup of fundamental particles, quarks, gluons, electrons, and photons, all moving chaotically. This era is known as the quark-gluon plasma phase. At this stage, the universe was a hot, dense plasma. In this plasma, photons, the particles of light, were trapped. They couldn't travel freely because they kept colliding with free electrons. This constant scattering of light made the universe opaque, similar to how fog scatters light on Earth. Think of it like this. When you're driving through dense fog, the light from your headlights scatters in all directions, making it impossible to see far ahead. This was the universe's condition during its first 380,000 years. Light couldn't escape or travel far without being absorbed or scattered. Chapter 2. Recombination. The universe becomes transparent. As the universe expanded, it cooled. By the time it was 380,000 years old, the temperature dropped to around 3,000 Kelvin. Hot by today's standards, but cool enough for protons and electrons to combine and form neutral hydrogen atoms. This moment is called recombination, and it changed everything. With fewer free electrons, photons were no longer scattered. They could travel freely across space, creating the first visible light of the universe. This is the cosmic microwave background radiation, the afterglow of the Big Bang. It's the same light that's been traveling for 13.8 billion years, reaching us today. Chapter 3. Redshifting. From visible light to microwaves. Originally, this light was in the visible and infrared part of the spectrum, but as the universe expanded, it stretched the wavelengths of this light. This is known as cosmological redshift. Today, the CMB has been stretched so much that it falls into the microwave region of the electromagnetic spectrum. Hence the name cosmic microwave background. At a temperature of just 2.7 Kelvin, just above absolute zero, the CMB is incredibly faint but still detectable across the entire sky. It's the oldest light we can observe and a direct window into the early universe. Chapter 4. Mapping the CMB. Tiny fluctuations that changed everything. When scientists first detected the CMB in 1965, they discovered something remarkable. It wasn't perfectly uniform. There were tiny variations in its temperature, just a fraction of a degree. These fluctuations represent differences in density in the early universe. Denser regions had slightly stronger gravitational pulls, attracting more matter and eventually forming the first galaxies and galaxy clusters. These fluctuations are the seeds of the cosmic structures we see today. Chapter 5. What the CMB tells us about the universe. By studying the CMB, scientists have unlocked some of the biggest mysteries of the universe. For instance, the universe's age. The CMB tells us the universe is 13.8 billion years old. The universe's composition. It revealed that 68% of the universe is dark energy, 27% is dark matter, and only 5% is normal matter, the stuff we're made of. The shape of the universe. The CMB confirms the universe is flat on large scales, meaning its geometry follows the rules of Euclidean geometry. The rate of expansion. The CMB helps us measure the Hubble constant, the rate at which the universe is expanding. Chapter 6. The CMB's role in modern cosmology. The CMB is far from being just a relic of the past. It's a cornerstone of modern cosmology. Ongoing studies aim to answer questions like, what caused the tiny fluctuations in the CMB? What role did inflation, a period of exponential expansion, play in shaping the universe? Can we find evidence of primordial gravitational waves in the CMB? These could tell us more about the universe's earliest moments, even before the CMB was emitted. Conclusion. Thanks for joining us on this deep dive into the cosmic microwave background radiation, the universe's oldest light. If you enjoyed this journey, give this video a thumbs up, subscribe to Stellar Studies, and let us know in the comments what cosmic adventure you'd like us to explore next. Until then, keep exploring the stars and the science behind them. This is Stellar Studies signing off.